Second paper is a two-layer blockchain sharding protocol leveraging safety and liveness for enhanced performance. This is from Yibing Xu, fourth year PhD student at the University of Copenhagen.
Thanks for the introduction. Good day, everyone. My name is Yibing Xu. I'm a PhD student from the University of Copenhagen. I'm excited to present our work named two-layer blockchain sharding protocol leveraging liveness and safety for enhanced performance. This is a joint work with my esteemed colleagues from the University of Copenhagen, Jing Yizhen, Boris Daughter, Ted Slats, and Yongran Zhou. Boris and Yongran are here today as well. So, before diving into the intricacies of our protocol, let's briefly discuss traditional blockchain systems without sharding. So typically, a single leader server is chosen periodically to propose a block, which is then voted upon by all services. So while simple in concept, this approach encounters scalability issues as the number of servers grows. Increased server count translates to higher data and computational demands for individual nodes, diminishing efficiency, right? And cool. Each node must verify each block, so you could not extend the block size without increase the data demand for individual nodes. Right. Okay. So to address these challenges, existing work draw inspiration from sharding, which is a database concept to reduce the workload on individual nodes and boost overall performance. Sharding involves partitioning nodes into distinct shards, each forming its own blockchain. This allows for the parallel existence of multiple shards as the number of nodes increase without overburdening any single node. Right. So numerous sharding designs already exist, such as OmniLegit, which is an asynchronous protocol, and Reticulum, which is one synchronized communication protocol. These designs typically involve randomly assigning nodes to shards and executing separate Byzantine fault-tolerant protocols within each shard. So apparently, it is possible that a shard generates incorrect results if the adversary dominated the shard. So that is to say, they outnumbered the number of nodes in the shard to the extent that they can reach a decision without the approval of any honest node. Then a more precise security question for sharding is how large a shard needs to be to avoid such a security concern. Right. So we calculate the probability of an adversary compromising a certain percentage, PA in this case, of the overall population, gaining control of more than half of nodes in a shard of size M. This probability must be lower than a threshold security threshold sigma, like guiding our choice of the shard size M. In another word, the size of a shard is determined by the security parameter sigma and the overall population, adversarial population PA. So now if we want more shards, then we need to reduce M, or the size of the shards. Then the more convenient way of thinking is to increase the bar for a consensus decision in each shard. That is, not only we want at least half of the nodes in a shard to agree on something, we want 2/3 or 5/6 of nodes to agree on the same thing. Then to fulfill the same sigma for this equation, we may allow reduce the M, right? So, however, with this increased bar for a decision, there comes liveness issues. Let S be the maximum percentage of nodes being adversarial that is allowed in a shard in order to generate a correct verdict, and L be the maximum percentage of nodes being adversarial and is allowed in a shard in order for the shard to generate a verdict. Then, like for this normal synchronized communication shard, in this example, we have 5 nodes, right? So 2 of them being adversarial. A decision is reached when at least 3 nodes agree to it. But in a case with, let's say, S equals to 80%, that means that in this case, we need all 5 nodes to agree on the same thing before decision can be reached. So it is true that only the adversary taking all 5 noses can enforce a wrong decision, but the adversary even taking only 1 node in the system can force the shard to not reach a decision anymore. So this implies that decision requires both the help of the honest and the adversary noses. Right. So, yeah. So there are also existing works for sharding that adjust the liveness and safety threshold. They add an additional component to relive the shards when the shard encounters liveness issues. So in this 2020 work, when the shard is dead, all noses are reassigned to different shards. The number of shards is adjusted or reduced in most cases. And in this 2022 work, the gearbox, when a shard is dead, only this shard is rebuilt with a larger shard size. The number of shards is not adjusted. That means that the shards are overlapping with each other. So with some noses being the members of multiple shards, this will bring additional workload for the shards. Right. Okay. So let's say if we only adjust the shard size by the number of shards, it will result in a huge overlap among the shards. For example, if at the beginning all shards are set to tolerant error equals to 10%, and there are actually 33% of adversarial noses attacking on liveness, more than half of the noses are in 8 shards simultaneously. This implies that 8 times of workloads for a single node. Right. So. Right, it also has like security issues because we know that either the synchronous or asynchronous version of communication model only guarantees that the honest noses receive the message from each other. There's no guarantee that from the adversary noses or the adversary message will be received at all. And because we need help from an adversary to reach a verdict, there's no guarantee that the adversary voices are received by other noses. This will cause deviation among the honest noses. Some believe that a verdict is reached, while the other does not believe in it. So let's take an example. So like admittedly that the consensus protocol requires multiple phases of voting, like pre-commit or commit, things like that, right? For illustration, we assume there's only one round of voting. So let's say here, there's only one honest node in this shard, and it votes to accept a block, right? So, however, all other nodes remain silent to this node, right? So now that after timeout, a new block is proposed, right? So then this honest node vote again for this new block, right? So because the O1 did not reach a consensus to their knowledge, right? To its knowledge. Now that the other nodes vote for both blocks, right? So in this case, we will have 2 accepted blocks of the same height, which is not allowed. Right. So because the nodes outside the shard is not listening to the voting inside a shard, they cannot tell if a vote was casted on time or not. Thus, they cannot tell if they cannot decide on one block between these 2 blocks, and they cannot punish the nodes for double voting, right? Because it's indeed possible that the first block was not receive enough votes at the time. So. So people may say that protocols like hot stuff, which uses the threshold signature and asks the leader node to transmit all the votes, you don't have these differences in votings for different nodes, right? So however, in order for the protocol to work, it would require enough nodes to follow the rules of voting between the phases. So this is actually the same thing here, because there's no guarantee that the adversary nodes will do that. Okay, so that's. Overall, the adversary nodes cannot force a wrong decision. They can still cause equivocation. This is because the honest nodes may fail to align on the fact that if a block is accepted or not, right? So yeah, it all comes to this question, like how can a shard reach an honest consensus independently with the presence of the majority adversary nodes, right, inside the shard? So introducing Reticulum, so our innovative 2-layer blockchain sharding protocol that prioritize both safety and liveness. Nodes participate in both a process shard and a corresponding control shard simultaneously. The process shard runs a error equals to 0% system, which means that in order to accept a block, all nodes of this process shard must vote for this block. And the control shard runs a error equals to S, but it's less than 50%, which is a normal synchronous communication shard, and it can reach the consensus independently without having any equivocation problem, right? So rules are simple. So if a block does not receive the unanimous vote within the process shard, then this block is transmitted to the control shard for additional voting. And how do we know if the block received the unanimous vote or not? We use the Byzantine broadcast, right, which ensures that if a vote is broadcasted, then all honest nodes will receive and acknowledge the vote, right? So then a node inside a process shard, when the node inside the process shard votes, its vote is Byzantine broadcasted and received by all nodes in the corresponding control shard, right? So it is one synchronous communication system. So we have two time bounds, T1, which is used for the voting within the process shard, and T2, which is used for the voting within the control shard. T2 is dynamically adjusted according to how many process shards that need to be verified in the control shard. So because we already used the Byzantine broadcast for the votes, there's a consensus on which nodes is voted in the process shard and which nodes did not vote in the process shard. Thus, we may build credit systems and have punishments towards silent nodes and nodes that voted for a wrong decision, things like that, right? So we use this design called tau liveness guarantees, which assumes that all honest nodes are remain active at all time, but we allow other nodes to abstain from voting in the process shard once in every tau rounds of voting. This is to allow the network to make mistakes, also to introduce additional redundancy for the network, right? So then we follow design 4 strategies for the adversary. So bank 1, which assumes that all adversary nodes do not vote for the process shard at the same epoch. So bank 1 will only occur once in every tau epoches. Otherwise, the adversary nodes will be expelled, right? And the average, which is very simple, that each adversary node does not vote once in a random epoch in every tau epoches. And the worst, so because the process shard requires the unanimous voting, right? So you only need one silent adversary node in each process shard to completely pass all the process shards for one epoch. Thereby, it can stop I epoches in every tau epoches without violating the tau liveness guarantee, where I is the number of adversary nodes in a shard. And then lastly, we have this 3 cycle, which is based on the worst strategy. But all adversary nodes vote at most tau minus 2 epoches in every tau epoches and being expelled at the second time when they remain silent in voting, right? So we did experiments for 5,000 simulated nodes, and we applied the different strategies. So the baseline throughput here refers to the performance of a rapid chain-like protocol, because the worst performance of our case is that when all process blocks fail to be accepted and they are being decided in the control shard. This is similar to rapid chain, where there's only one layer of the shard, and the size of the control shard in our case is the same size of the shard in rapid chain, right? So as you can see that in most of the cases, we largely outperformed rapid chain-like protocol. So we also compare with the performance of Gearbox. However, we must emphasize that Gearbox is not secure, completely not secure, because of the equivocation problem, right? So they do not initiate a new epoch within a shard after being the block being finalized. So there will be equivocation problems, right? So because and the leader node of its control chain, which is a chain that maintained by all the nodes, can decide the life or death of the shards arbitrarily because of the equivocation problem. Now you can choose from these things, right? So there's no consensus on if a shard is alive or dead. So it is the opinion of the leader of the control chain only, right? So even disregarding the security issues, Gearbox has this reduced performance because it has huge overlaps among the nodes. The nodes need to deal with multiple workloads simultaneously according to this PA run, which is the adversary population in runtime. And as you can see, we outperform them most of the time. And this experiment is a result even like disregard layer cost for making adjustments to the shot size, things like that, right? So that's it. Thank you, and I'm open to take questions.
Hi, this is Genting from Purdue University. So I have two simple questions. First, is the control shot overlap with the processing shot? And the second question is how to create the control shot.
Right. Okay. So the control shot is actually overlapping with the processor. You can see that the control shot actually embed all these processors, so they have this. So each processor has a control shot that's governing its processor, right? So in that case, it's overlapped, right? So sorry, what's your second question?
The second question is how to create the control shot.
Right. So it was very simple, right? Just use the same as how you could create the processor, just randomly assign them according to like a random ID or obtained like.
So is it the same as
Yes.
the formation of processor shot?
Yes, it's the same, just different insides.
Thanks.
Thank you.
Lachlan Gunn from Alta University. So when you evict a silent node from the processing shard, how do you kind of regenerate things? Because it seems like depending on exactly what your kind of synchrony model is, couldn't it be possible that some adversary could then try to cause the honest nodes to be rejected from, or to be evicted, sorry, from the process shards, to essentially do a takeover?
Sorry, it's because probably.
Sorry.
Okay, sorry.
Yeah, I'm sorry. Yeah, so when a node gets evicted from a shard, so do the thresholds for like how many messages you need, do they stay the same, or does the size of the shard
Okay,
reduce?
so yeah, okay, I understand the question. So if say a node is expelled somehow, right? So in that case, we do not adjust any threshold because in our assumption, all honest nodes are stay online active at all times. So if they are expelled, then we somehow consider them as adversary nodes. So in that sense, we do not adjust any threshold for that.
In that case, what ends up being the synchrony assumption of the entire protocol? Because it seems like you start off with an underlying BFT protocol that could be asynchronous, but this seems like it makes the protocol kind of synchronous now.
Yes, we actually find that when you adjust the liveness and safety, you cannot make that asynchronous, right? Because you do not know this additional additional voices will be received or not, right? So there's a no time bound or no restriction for these adversary voices, right? So in that sense, you must have a time bound. So all the voices that is not received by that time bound is somehow disregarded, and in that sense, we must have this synchronous bound for that. And the problem is like Gearbox claimed that they can use this asynchronous thing, but it really does not work in that case.
Okay, thank you.
Thank you.
I also have a question regarding the thread model. So you mentioned, so from the slides, it seems like you use like a silent node is a kind of an adversarial node, right? So
yes.
How do you detect such a node in a large scale setting?
Okay, yeah, so like we use the Byzantine broadcast, right? So in that case, if you actually broadcast a vote, there will be a consensus for if this vote is received or not. So in that sense, we could like detect that if a vote is received or not. And in order to make that cost more, the way we do that is to restrict all these voices the broadcast of these voices within the corresponding control shard. So instead of broadcasting the voices to all the nodes, we just broadcast them to the corresponding control shard. So in that case, we just reduce the cost for the Byzantine broadcast. But through Byzantine broadcast, we gain the ability to detect if the votes are received or not. Thank you.
Let's thank the speaker again.